Yes, Miss, we're hearing you.
Okay, good. Thanks, Nashan. Are you seeing the screen as well?
Yes, Miss.
All right, wonderful. Thank you. So last week we started looking at non-parametric tests, and the first one in the series was the sign test. And we said the sign test is really just concerned with assessing the difference between two paired groups. It's a non-parametric analog for the dependent or the paired t-test. So we can apply a sign test if our data does not follow a normal distribution, because as we know, in applying non-parametric tests, our distributions do not have to follow any particular pattern, specifically that concerning a normal distribution. We also learned that the sign test is one of those tests that tend to waste data a bit, because for the sign test, the magnitude of the differences are not considered. The only thing that's considered is the sign of the differences that we would have obtained. Now, this morning, we are going to be looking at the Wilcox assigned rank test. And this test is also a non-parametric analog for the paired or the dependent samples t-test. So we're gonna go right into it. And as we go, you're gonna see some of the differences and similarities with the sign test. All right. So for today, as usual, we're gonna look at the test statistic, the Wilcox table, and we're also gonna look at approximation to Z if we have to carry out this test on a sample size that is large. And then the final thing we're gonna do for today is to use SPSS to perform the Wilcox assigned rank test. All right, so we kind of said some of this before, but I'll say it again just for emphasis. For your Wilcox assigned rank test, it's also called the Wilcox matched pairs test. You may also see in some books the Wilcox's T, uppercase T, Wilcox's T test. So remember the regular T test is lowercase t. So you may see the Wilcox's uppercase T test. And it's also for two dependent samples. It's the non-parametric analog for the paired lowercase t test. And for the Wilcox assigned rank test, the variable of interest should be at least at the interval level. So your variable must be measured at the interval level. Remember, for the sign test, what's the lowest level of measurement for the sign test? Nominal. So you can actually do a nominal, you can use nominal variables for your sign test, but for Wilcox assigned rank, the variables need to be at least at the interval level. So the sign test, it says, is more, the Wilcox assigned rank test is more powerful than the sign test because it actually takes more information into account. So it takes into account the magnitude of the differences as well as the sign of the differences. As opposed to just looking at the sign, it also takes into account the magnitude of the differences. In terms of hypotheses, the hypothesis for the sign rank test on the null hypothesis is that the mean rank, so now we're introduced to something different, a new term, the mean rank, so you'll know what these are later on. The mean ranks of two dependent samples are equal. And then the alternate hypothesis says the mean ranks are not equal. You may also see, for your null, the median difference, uppercase M, is equal to 0 for the null hypothesis. And then the alternate hypothesis would be that the median difference is not equal to 0. All right. Now, how do we determine the Wilcox's T? These are the steps. There are 6 steps.
Sorry,
I'm gonna read them
could you
through.
repeat? Could you repeat the difference between the null and the alternative, please?
So there are two ways of looking at the hypothesis. You can talk about the mean ranks, or you can talk about the medians, the median difference. So mean ranks, you'll meet it later on. You don't understand what it is yet, but you'll see it later on. So the first one is that the mean ranks are the same. So you're gonna have two groups, or two groups before and after, and you're gonna determine the ranks, you determine the mean ranks, and you're saying if the mean ranks under the null, the mean ranks are the same. The alternative is that the mean ranks are not the same. And then there's another way of looking at the hypothesis where you can look at the median difference. So if you remember the t-test, the paired t-test, what we did was to take the differences, then that list of differences became our new data set, and we said that the mean difference should be 0 under the null. But this time, we're saying that the median difference is gonna be 0 under the null. That's fine, Vanessa?
Yes.
All right, so when you get to understand what the mean rank is, hopefully it should be a little clearer. All right, so in determining the Wilcoxon's T, the first thing that we're gonna do, we're gonna list the paired scores in two columns. So we're gonna have, let's say we have a before and after case, we're gonna list them in two columns. Then we're gonna determine the differences. So we're gonna create a third column, and that column is gonna have our differences. And remember, it's important for us to define our differences, to understand what we should be getting with our differences, and to be consistent. So we can't have some before minus after, and then some is after minus before. We have to be consistent. And then the third thing that we're gonna do, if we get zeros for any differences, we're gonna delete those zeros. So we're not gonna consider it. We're gonna delete the zeros, and we're gonna reduce our sample size. Then the fourth thing though, we're gonna rank the differences from smallest to largest. In ranking the differences, we're not taking into account the signs, because you know negative numbers are smaller than positive numbers. So in this case, we're not gonna take into consideration the signs. We're just gonna look at the absolute values, and we're gonna rank the absolute values from smallest to largest. If in any circumstance you have two differences of the same value, so let's say you have two differences of threes, you're gonna go through, assign ranks to them just normally, and then in the end, you're not gonna leave them like that. You're gonna take the average of the two ranks, and then you're gonna assign both ranks the same average. You'll see it. You don't have to stress about it. There's an example and you'll see it. Step number 5 now. T is gonna be the smaller of the sum of the ranks. So after you've assigned the ranks, the next thing you're gonna do is assign what? After you've ordered your numbers, you've assigned ranks, the next thing you're gonna do is to put back the signs on the ranks. So the ranks are gonna take the signs of the differences, right? And then you're gonna separate them into two groups. You're gonna have negative ranks and positive ranks. Good? And then you're gonna take the sum of the negative ranks, not taking the sign into consideration, the sum of the negative ranks, and then the sum of the positive ranks. Whichever of those two sums are the smaller, that's gonna be your computed T, or that's gonna be your Wilcoxon T. Good. And then number 6 now is what we use to come to our conclusion. So it says, if the computed T is equal to or less than the critical value in a table of the distribution of Wilcoxon T, then the two samples can be said to differ significantly. So it says, in actual practice, computer programs like SPSS compute the probability of a standardized signed rank difference Z for the researcher without the need for us to be consulting any tables. But for today, we're gonna do it both ways. So we're gonna use the table as well as we're gonna use the software. So just in case if you ever have to use a table, you know how to use the table. Which what? Go again. Both as in what? Both as in what?
As in to demonstrate it with a table as well as with SPSS.
No, usually just SPSS. Usually just SPSS in the exam. Or if you come and you want to talk about the table, depends. But usually just SPSS, because after this, people hardly consult tables, but you just may never know what you'll have to do in life. All right, so here's our example. So we're using the same example from the last class. And the example from the last class was a case where some researchers wanted to determine whether a certain drug lowered blood pressure. So here we're looking at a one-tailed test. So they wanted to know if a certain drug lowered blood pressure. So as we've seen last week, we have our subject ID in the first column. So 1 to 10, there are 10 persons in the study. Then we took their systolic blood pressure readings. So for example, patient number 1, their initial SBP was 166, number 2, 135, number 3, 189, and so on. And then the researcher administered the drug and determined their SBP again. So we have the third column, post-treatment SBP. So 132 for patient, 38 for patient 1, 120 for patient 2, 176 for patient 3, 180 for patient 4, 160 for patient 5, and so on. And so once we've listed our before and after values in our columns, the next thing we want to do is to define our difference, determine the differences. So for us, the difference is defined as baseline minus treatment. And we know in this case, if the drug lowered blood pressure, then we're expecting to get more positive results. Because it means that SBP after treatment should be lower than the baseline. Good, so we found our differences. The next step is to rank the differences. We're gonna rank our differences. But before we rank them, we actually need to put them in numerical order. So this is me just putting them in numerical order, just for your sake, so that you can see them. So 4, 4, 8. So in ranking, in ordering them, you do not consider the signs, just the absolute values. So 4, 4, 8, 12, 13, 6, or 15. 15, 16, 24, 28. So here, remember, whenever we have 0, so 180 minus 180 gave us 0. So we do not need to put this in the ordered pairs. We're gonna ignore, and our sample size is gonna be reduced by 1. So we've ordered the data, and after ordering, we're gonna assign ranks. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So let me just write this here in case somebody looked away from the screen and they don't know what is going on. And these are the ranks. So the instruction,
You said you have two bodies that have the same difference. What you say you're going to do this?
I'm gonna do it right now.
So you have like the 2 squares and then.
That's fine. I was just about to say it. So the instruction says that if we have differences that are of the same value, what we're gonna do is to take the average of the ranks. And then we're gonna assign that average to both differences. So this is 3. So 3 divided by 2 should give us what? 1.5. So it means the correct rank for these guys is gonna be 1.5. And everybody else remains the same. So if you see here, I've ranked the differences. So these values are what I have right here, the initial ranking system. So you should be able to pick up that. But now we need the final ranking system.
Sorry,
So the
so we
final
got
ranking
1.5.
system. What did you say, Vanessa?
Could you repeat how we got 1.5 and why we did that?
Okay, because we have 2 differences that are of the same magnitude. So there are 2 4s, 1 here and 1 here. So once you have 2 data points that are the same, you would rank them regularly, but in the end, the final ranking is gonna be the average of the two ranks. Similar to what we did when we did Spearman's rank correlation. So it's 1 plus 2 give you 3 divided by 2. And whatever that average is, you're gonna assign it to both of the data pairs.
Miss, but why would you say they have the same magnitude if one is negative and one is positive?
Because we're in a ranking, we're only considering the absolute values. We're not considering the signs. The signs will come in a little later.
Okay, gotcha.
All right. All right, good. So this was the initial ranking system, but then the final system is gonna be, so 28, so a difference of 28 is gonna have a rank of 9 still. We're not gonna change that. So guys, if the table on the handout is too small, I printed some larger tables that you can write on. If the handout is. I took out the zero. So remember, we started with 10 people. We started with 10 patients. And so this patient, their blood pressure didn't move. Their blood pressure didn't move. So they had a difference of 0. So once you have any 0 differences, and especially because it's just 1 0, we're gonna not consider that patient and reduce the sample size by 1. You missed a number, okay. All right, fine. So 28 is gonna have a rank of 9, see, it's right here. The next number is 15. 15 will still have a rank of 6. The next number, 13, it's gonna have a rank of 5. 4 is gonna have a rank of 1.5. So we don't need that one. So 4 is gonna be 1.5. 8 is still gonna be a rank of 3. 24, still gonna be a rank of 8. 16, 7. 4 is gonna be 1.5. And then 12 will still have a rank of 4. So the only change is for those that had similar magnitudes. These guys are the only change that are there. Good. So once we've done the ranking system properly, the final step is to assign signs to the ranks, Vanessa. So now it's time for us to assign the signs to the ranks. So in assigning the signs to the ranks are gonna take the sign of the differences. Good? So for example, 28 was a positive 28. So that rank is gonna be positive 9. 15, a difference of 15 was positive, so that means the rank is gonna be positive 6. 13 was positive, so this rank is positive 5. We're not using patient number 4. Patient number 5, their difference was -4. So this 1.5 is gonna be a negative 1.5. Patient number 6, they had a difference of -8. So this is gonna be a rank of -3. 24, that was a positive difference. So that's positive 8 for the rank. 16, that's positive. So the rank is positive 7. 4, this 4 is positive. So the rank is positive 1.5. And the final one, a difference of 12. That's positive. So the last rank here is gonna be positive 4. Any questions on this before we move on? Vanessa, are you okay? Anybody else online? Are you okay?
I'm looking, but I think we're kind of confused.
Okay. All right, so we can go over. So now that the table is filled out, we'll go over. I'll use the next table to show you. It's there. So remember, the Wilcox assigned rank test is a test of the non-parametric test that allows us to find out if there are differences in our paired samples. A case, a before and after case, is a very good example of such a scenario. So we know that we are looking at blood pressure before a certain drug was administered and blood pressure readings after this drug was administered. In using the Wilcox assigned rank test, we are instructed to first outline our data points in 2 columns. So we have our before reading, we have our after reading. So these 2 columns should be good for you. The next thing we're gonna do is to determine the differences of the data points in the 2 columns. So we're gonna subtract, for us, we're subtracting the post-treatment from the baseline treatment. So this 3rd column here gave us our differences. The next thing that we need to do is to rank the differences and we're ranking the differences because this test actually takes into account the magnitude of the differences, so to speak, indirectly. So we are ranking them, and in ranking them, we need to look at the absolute values of the differences. So when we're ranking, we're not thinking about if the differences were negative or positive. We're just gonna rank them, order them. We're ordering them first, ordering them from lowest to highest, and then we're gonna assign ranks to them. So this is what we did here. So we've ordered them down here. So this is the order data. So all of these are the differences. Top row here that we just wrote in. These are the differences, we've ordered them. And then we gave them a rank. So we ranked them from 1 to 9. And then now the instruction said that if there are any differences that are the same value, you're gonna take the average of the ranks and assign that average to both of the ranks. And even if it was like 3 4s, then whatever the average worked out to be, we would still assign that value. So it would be 5, 1, 2, 3. Yes, so it would be 6. So it would be 6 divided by 3. And so the average would have been 2. And so it would give the 3 4s a rank of 2. But that's not the case. We just had 2. So it's 1, 2 divided by 2, 3 divided by 2 gave us 1.5. And so what we did was to say, in this column, so this column, you really don't need it. I just put it there. So that's just us ranking it initially, but this is the one that we actually need, this last column here. So what we did was to take the average for these 2 and we inserted their correct ranks, because these are the only 2 ranks that changed from this list. If you notice, those are the same values. These ranks are still the same. The only ones that changed are the ones that were similar for this column. And this is actually the right column to use, this one. And then now the last thing we did was to assign the signs to the rank. How do we assign the signs? We assign the signs by looking at the signs of the differences. So all the differences that were positive, their ranks are gonna be positive. All the differences that were negative, their ranks are now gonna be negative. That's fine, Vanessa?
Yes, miss. What's this now? Number 5 and number 9. You just randomly assign 1 or 2 to any one of them because they were both 4s, but one was negative and one was positive.
No, remember, in ordering, it doesn't matter if they're negative or positive. So yeah.
So how you determine which one get number 1 or which one get number 2? It don't matter.
It doesn't matter. It doesn't matter.
Okay.
It doesn't matter because we're not looking at the signs. I just put it there. Doesn't matter. At the end of the day, they're gonna have the same rank. So it really doesn't matter. And the only thing that might be different is the sign. Good. So that's that. So the next step for us is to determine the sum of the ranks. So this is where the sign comes in. So the signs are only used to create two groups. So we're gonna have a group of negative ranks and a group of positive ranks. That's the only thing the sign is doing. Even in determining the sum, we're not taking the signs into consideration in terms of, we know if we're subtracting if we're adding a negative number to a positive number, we're gonna subtract and the sum is gonna take the sign of the bigger number. We're not into any of that. We're just using the signs to group them. So if we were supposed to take the sum of all the positive ranks, which for us is 9 plus 6 plus 5 plus 8 plus 7 plus 1.5 plus 4, we would get a sum of 40.5. And if we were to take the sum of the negative ranks, which is 1.5 plus 3, we would get a sum of 4.5. So these are our negative ranks. It's a sum of 4.5. So we've taken the sum of the positive ranks and the sum of the negative ranks. So let's think about it. If the drug has no effect on SBP, what would we expect? We would expect half the post-treatment values to be high and half to be lower than the corresponding baseline values. So in addition to that, we would expect the magnitude of the increases to be about the same as the magnitude of the decreases. Thus, we can expect the sum of the signed positive ranks to be about equal to the sum of the signed negative ranks. So let's take the sum of these values. So if the drug made no difference, we expect that under the negative ranks, we're going to have some low readings and some high readings. Under the sum of the positive ranks, we're going to have some low readings and some high readings. So I just kind of group these figures together so that you can take the sum of each and just tell me what you get. So 2.5 for the positive. And 22.5 for the negative. So that's what we're seeing. If things were happening at random, the drug makes no difference. We're expecting the sum of the negative ranks and the sum of the positive ranks to be just about the same. So that's under the null hypothesis. Now, in real life, we always need to find what the sum is going to be. What is the expected sum in our scenario, in our situation that we're dealing with? And so we have this as a formula here that should help us to find the expected sum in whatever circumstances we are in. So that's the formula, n into n plus 1 divided by 4. You can go ahead and apply it and let me know what you get. When you use the formula. 9. So pick out the 0, reduce the sample size by 1. 10. All right, good. Well, that's the formula you use to determine the expected sums. Good. All right. Now, by definition, the test statistic in the Wilcoxon signed rank test is the smaller sum of the positive ranks or the negative ranks, called T, and it's uppercase T. In some sources, you may see the Wilcoxon W, uppercase W. So for positive, it's W plus, so superscript plus. If it's a negative, it's superscript negative. So what is this saying? When you've taken the sum of the negative ranks and the sum of the positive ranks, whichever of those values is the smaller one of the two, that's going to be your computed value. That's the computed value that you're going to compare to the value that you get from the critical table. the table of critical values. Yeah, that's the right term. So you may see uppercase T or uppercase W for the symbol. Yes. Yes.
Or here we have it, therefore sum of negative racks greater than 1.5.
It shouldn't be greater than. It's like, you know, like a little arrow. That's what it should be. It's not really greater than. It's supposed to be like an arrow.
Well, how do you do it?
Thanks for even pointing that out. How do I get one?
Alright, so examination happens. When you have for the negative rack, 1.5 plus.
What's the question?
Assign those to show you that it would be the same.
Right. Right. It's not necessarily for the data. This is just FYI. See, it says aside. So it's not really continuing with our assessment. So all I'm saying is under the null, for the negative ranks, you're going to have some low values. So right now we have this one, low values, and we have some high values. And then for the positive ranks, we're going to have some low values and then some high values. And if once that is the case, then the sums are going to be the same. And once the sums are the same, then we're saying there's no difference between, the drug doesn't make a difference. So that's all I did. I just put it there. So you can see it numerically if you're that kind of person. That's all. It's not really a long oral assessment. So now we're going to go back to our assessment, which is right here, finding our computed T. So we did say, or the instruction said that we should let T be the smaller of the sum of ranks for the positive differences or the sum of ranks for the negative differences. And we did the sums already, and we know that the sum of the positive ranks was 40.5, and the sum of the negative ranks was 4.5. The smaller of these two sums is our test statistic. So in our case, what is our test statistic? 4.5. So our test statistic right now, our computed T is 4.5. So this is the value that we're going to compare with the value in our table of critical values. So this is us going off track a little again. It says when any small, we're going to use this statistic, what we just did, the smaller of the two sum. Then, just remember it says when T is the smaller of the sum of the positive or negative ranks. To draw a conclusion, we're going to compare that observed statistic to some critical value, just like we know to do before. And that critical value is found in the Wilcox assigned rank test table. So you should have that for those who are online. And those are in the classroom, they should have a hard copy. So the question for us is, did our drug lower blood pressure? So we know what the sum of the negative is, 4.5, the sum of the positive, 40.5. This is a solitary repeat. And we know that T is 4.5. Now N is 9 because we deleted the tie and we adjusted the sample size by 1. So where is the mouse? Oh, so we know that N is 9. So now we're gonna go to a Wilcox assigned rank test table and we are gonna check to see if there is a statistically significant difference there. So this is our table. So we're carrying out this test at N equals 9. Alpha is at 0.05, and we are looking at a one-tail test. Wonderful. So what's the critical value that you have there? 8. 8. And just in case we don't remember, all right, somebody's trying to get me this. Just a second then. I'm sorry about that. So our critical value is 8. And just in case you forget how to interpret, the notes are down here. It says number 2 is what we're interested in. It says reject the null hypothesis if the test statistic T is less than or equal to the critical value found in this table. And then it also says fail to reject the null hypothesis if the test statistic T is greater than the critical value found in the table. So what's our conclusion gonna be? The drug lowers blood pressure. So I guess before I get to conclusion is decision. What's our decision? Sorry. Let's start with reject. So we're gonna reject H0. So because 4.5 is less than the critical value of 8, so we're gonna reject H0 and we're gonna conclude that the drug actually lowers blood pressure. Wonderful. You want to go back?
No,
Okay.
according to the science.
That's what we said, and we'll talk about it a little later. There's a slide for that, for comparing the two. I hope you have the answer for your question. All right, so I actually did write it out already for you, so that's good. Wonderful. So our decision is to reject H0. Our conclusion is that this drug actually lowers blood pressure. So good. If our N was large, if it was greater than 30, we could actually use our Z table to determine what was actually going on. And if we were going to use our Z table, we would need this fancy formula that I also printed another sheet so you can write it on it properly if the handout is too small. The formula is E is equal to T minus N into N plus 1 divided by 4 all over square root of N into N plus 1 multiplied by 2N plus 1 over 24. So as usual, we have our observed minus our expected. So remember, this was the formula for expected over some kind of deviation, standard deviation. So this denominator is how they determine the standard deviation. And as usual, we're not getting into we're not concerned about how the formula was derived. We just need to know how to apply it. But just pointing that out to you. So that's the formula. So if we were supposed to apply this to our example, we need to apply this formula. Oh, sorry guys. Sorry. Hi, Hannah. Hello, Hannah. Yeah, we can go ahead and apply the formula for example. How did it it, Jody, or you just sit it on. Apply this formula to our example. If we're gonna do that, it's C is equal to, okay, let me just write back the formula so that we can know what the values are. T minus N into N plus 1, 4 square root of N plus 1 multiplied by 2N plus 1 over girl. All right, so let me just catch up, Krista. Thank you. Anybody else got anything different? All right. What did you get, Krista? 2.5. Double check again. Let's go. So T is gonna be 4.5 minus 9 into 9 plus 1. And Christian already told us that that is 22.5.
How many square root?
Okay. All right, and then it's gonna be 9 into 9 plus 1 multiplied by 2 times 9 plus 1 divided by 24. So, numerator. So 4.5 minus, so we know that this part is 22.5 because we did it already. So it's 4.5 minus 22.5. Or maybe I should write it out. I'll write it out. All right, 4.5. 4.5 minus 22.5 divided by. So when you work out all of the denominator, what did you get? Square root of what? 71.25. All right, and so our numerator was what? 22 point, yeah, minus 18 divided by, so the square root of 71.25 is 8. Around 7 point a lot, or 8 point something.
What was the answer you guys got?
8.44. And therefore, Z, so we're getting to it now, Vanessa. Z is
Minus
equal to
2.1.
negative 2.1132. So Z is equal to negative 2.132. And then what? Everybody is okay? Everybody's on the same track?
Yes, ma'am.
All right. Wonderful. I'm just going to point out something to you. This is just FYI. If you're feeling confused, just drop it. Don't take it on. All I want to point out to you is that the expected sum or the sum of the negative ranks, 4.5. And then the sum of the positive is 40.5. 40.5.
Maybe there are two, you know.
It's okay. For some reason, I just feel like somebody's gonna be confused. Let's just drop it. All I wanted to say is that if we used, you can plug it in if you want. If we used 40.5 right here instead of 4.5, we would have gotten the same Z value. It's just that it would have been positive. That's all I wanted to say. So let me not complicate it. I will leave it at that. That's all. But it's just that the instruction says that the smaller of the two is what we should use. So that's that. So now we need to use our Z table. And we know that in using the Z table, we need to find out what are the cutoff points for us. So we have to go to our formula sheet, our trusty formula sheet. Okay, it's fine, I have it. I trust the formula sheet. So we need to find out what is the cutoff point for a lower tail test. Formula booklet. What's the cutoff point? A lower tail test. What's the alpha over 2? For a lower tail test at alpha equals 0.05. The cutoff point is negative 1.645. So we know from biostats 1, so this is the cutoff point. Then we're going to find out where did our Z value fall in relation to this critical value here. Our Z value fell somewhere out here. So it's negative 2.13. And we know, what do we know? So what would let's see what would our decision rule be. Sorry. So let's set up the decision rule. I'm not gonna go to say that you already know all of this. I mean, you know it, but just to refresh your memory. So the decision rule would have been, let me write it there. Decision rule. Reject H naught if Z is greater than, no, not equal, yeah, or equal to is on the rejection sign, greater than or equal to negative 1.645. And no, less than, because it's lower tail. Good, less than. Thank you. I like the sound of that. Do not reject H naught. Do not reject H naught if Z is greater than negative 1.645. So that's our decision. So based on what we've determined so far, computed Z of negative 2.13 is less than or greater than negative 1.645. It's less than. So therefore, we are gonna reject H naught. So it says our computed Z is less than our critical value. Therefore, we're gonna reject H naught. If we wanted to find the area remaining in the tail at Z equals 2.13, could we find that area remaining in the tail at this Z value?
Yes.
Yes, we could. And the area remaining in the tail is the same as what? It's gonna be our P value. Good. So how are we gonna find the area remaining in the tail at Z? So we need to go back to our Z table and we're gonna find out the area between the mean, should say mu and our Z value. So we need to find the area here. Let's see what the area there is. So we're gonna look for a Z value of 2.13. 2.13.
2.13, I thought it would have been negative 1.645.
No, man. Remember, 1.645 is the critical value. But we want to know when our computed value is on this chart, what is the area remaining in the tail? So we only use the 1.645 to compare with our computed value to say, should we reject H0 or do not reject H0? Then now, in order to determine the p-value, we have to determine the error remaining in the tail after we've plotted our computed value. All right, so we're looking for Z is equal to 2.1 on the left and 3 up here. So that's 3 here. So it's 0.4834. That's the area between the mean and our computed C. Oops. So the area here is 0.4834. And to find the area remaining in the tail, we're gonna subtract from 0.5, because remember, your Z curve is divided into 2 equal halves, so 50% on the left, 50% on the right. And if all of this is 50% and we know this portion, in order for us to find this portion, we're gonna subtract the known portion from the total. So 0.5 minus 0.483 gave us a p-value of 0.016. Based on this p-value, this p-value is greater than or less than our 0.05. It's less than our 0.05. So that's our one-sided p-value, 0.016. Good. You still writing, guys? Good? All right. So, based on the Wilcoxon sign-gram test, there shouldn't be any S on this. Please remove that. We reject the null hypothesis. So we reject the idea that the median difference is 0, or that the difference before and after administering the drug is 0. And we conclude that the typical systolic blood pressure is lower post-treatment than compared to baseline. So the question here is, what would be the two-tailed p-value? So the two-tailed p-value would be 2 times our one-tailed p-value. So it's gonna be 0.0332. Good? Everybody is fine? Even if we just wanted to say, did the drug make a difference? Our p-value is 0.0332, which is still lower than our alpha of 0.05. So even if it was a two-tailed test, we would still be rejecting H0. Wonderful. So we're at the final step, which is to use SPSS to run the Wilcoxon signed rank test. So I've already done most of the work for you. You have the database from last week. It's SDP. It's SDP 2023 or something like that. Go ahead, open that database, and then we're gonna go through the steps. Go ahead and open that database. Do the same. You call it, Nikki? SBP, yes. Oh, you're already open. We want to continue. Are we ready? SBP. Guys online, are you ready? You've opened your database?
I said away for just a moment. Which one?
Okay, so you're gonna open
Places are we opening?
SBP 2023. That's what, it doesn't matter what the year, it's the same thing. SBP data. And the leavings is beside it, you can open it in the meantime because we're gonna use the leavings as well.
Thank you.
You're welcome, Anne. Ready? All right, we're gonna go to analyze non-parametric tests, legacy dialogues, two related samples. Repeating, analyze non-parametric tests, legacy dialogues, two related samples. You're gonna click on two related samples. Analyze non-parametric tests, two related samples. And we want legacy, right? So we want variable 2 to be baseline because I think SPSS is gonna do variable 2 minus variable 1. So I'm gonna put, let me see. Okay, so we want variable 2. Let me just run it first before I give you the instructions. So this is post-treatment minus baseline, so we don't want that. So in variable 2, you want baseline. So you're gonna transfer post-treatment first, so that post-treatment can be variable 1. And baseline can be variable 2. If you've done it like me, you can use this arrow here to switch them around. So that variable 2 is baseline, variable 1 is post-treatment. We could go on options if we want to and tick off descriptives and quartiles. Just to look at it, you don't necessarily need it, but we can look at it and see what they look like. And what we're interested in is the Wilcoxon. So that's already ticked by default for me. If that's the case for you, we'll just leave it. If not, please do tick it off. And then we'll click OK. So or descriptive. I don't know, last week I got. It's okay. I don't know what to do it again. So these are our descriptives. So the mean systolic blood pressure is 150.6 plus or minus a standard deviation of 19.2. And the baseline is 160 plus or minus a standard deviation of 17.9, well, 17.8. And then remember, we have the percentile, so every 25th percentile, that's Q1, that's for systolic, for post-treatment systolic BP, 136, so that's Q1. And then we have the median, 151, we have Q3, 164. So same, we have those values for baseline as well, 142 for Q1, median 160, and Q3 177. I'm just pointing this out because sometimes instead of reporting the mean ranks, people tend to report the median. And then if you're reporting the median, you can report the median with the IQR. And you remember how we determine the IQR is Q3 minus Q1. So if you, this is something that could possibly come up in the exam. I'm just saying. So when we get to, I'll show you when we get to the interpretation of the final thing. It will make more sense there. So just remember that descriptive statement. How does yours look? All right. So this is really what we want to get to, this table and the other one that follows it. So our difference was defined as baseline minus post-treatment. Our negative ranks, 2. So we had 2 negative ranks. Remember that? One, good. And then the mean rank for the next, before we get to that, the sum of the ranks here, 4.5. You remember seeing that?
Yeah.
And then the mean ranks, how did they get the mean rank?
4.5
divided by 2. So that's the mean rank. So whenever you see mean rank, that's what it is. If you're going to report mean ranks, if you're telling people about mean ranks, that's what you've basically done. So when they say sometimes these things are so hard to interpret, it's because we're not really using the data itself, but we've converted it to ranks and now we're talking about mean ranks. So the idea is because we've ordered the data and then we've assigned ranks to them, the idea is the higher the data point, the higher the mean rank is supposed to be, which, Jody, what is wrong with you? All right, let me pause it for a little while. Let's do the positive ranks. It's okay. So negative ranks, 2 negative ranks. The sum of the negative ranks, 4.5. The mean rank for the negative ranks, 2.25. Then we have the positive ranks. We had 7 positive ranks. And the sum for those positive ranks was 40.5. And then we have the mean rank, which is 5.79. Let me just pause it right there. Good. Close that. The next table. Next table. So So SPSS is telling us that it used the Z distribution for this example. And the Z value that it obtained was negative 2.134. We've seen that before. You've seen that before? Negative 2.13? Yes, we've seen that before. And then our p-value, so this is our two-tailed p-value. Our two-tailed p-value is 0.033. Did we see that before? Yes, we saw that before. Wonderful. All right, so before I come back to explaining the mean rank, let us talk about something else. Let's go to Jabari's question, I think. I think that's where we are. Okay, so alternatively, guys, you could use this easy step, the one that tells you what to do with your p-value, if you feel like you need to, but we're not gonna do it today, because as I said, I don't want you to come in the exam and do that on the first try. But if you run into problems and you don't remember the other steps, you can always use that one. Huh? Well, yeah, Jody said you'll get more questions. Well, we'll see. Uh-huh. I missed that. I think I should leave it alone too. All right. So in reporting the Wilcoxon result, we could actually write it like this to say, a Wilcoxon sign rank test showed, why do I have ranks? A Wilcoxon sign rank test showed that treatment with the drug did elicit a statistically significant change in SBP. So that's if we're doing it at two-tailed. So the Z value is negative 2.13 and the P value is 0.033. And then right here now, this is what I was trying to talk about in the descriptive table. You can report the median to say the median SBP was 160 and 151 pre and post treatment respectively. So you should actually, you could report the median or the mean ranks. Good. So that's two-tailed. For a one-tail test. Okay, I need to say something else. So remember when we're reporting the medians, we need to report a measure of spread. So the median is the central tendency. We need to report a measure of spread. So this is actually lacking in IQRs. And in determining the IQRs, you'll need to use the same descriptive table. So you'd add the IQR to the medians here. And remember that your IQR is Q3 minus Q1.
So right where you have
So
minus the 1.5.
right. Right. So let me go back to the descriptive table and help you to put it together. So, oh, I didn't have to come here. I think I have it on this. But so in this case, so this is Q1. So this column is Q1. That's Q2 for your medians, and this is Q3. So you can report the IQRs as well. All right, and then for a one-tail test, which is what we are really interested in, the p-value would be 0.016, and our appropriate conclusion might be a Wilcoxon sign rank test showed that treatment with the drug resulted in a statistically significant lowering of SBP. And we have our Z value there and our one-tailed p-value. And here the medians are reported again.
I have a question, Miss.
Yes, go ahead.
If the median systolic blood pressures were already mentioned, why do we need to talk about the IQRs? Wouldn't the Q2 be the Q3 minus Q1?
No.
No, man. No. No, Q3 minus Q1 is not gonna give you Q2. Q2 is your median. That's the value that cuts your data set into equal halves. Q1 is the value that separates your data such that 25% of the data points fall below that value, 75% falls above that value. And then Q3 is the value that cuts the data such that 75% lies below that value and 25% lies above that value. So remember that the IQR is a measure of spread. The median is a measure of central tendency. And whenever we're reporting a measure of spread, central tendency such as mean or median. So for example, if we're reporting the mean, we would have reported something like the standard deviation or the variance. And when you're reporting the median, that's usually accompanied by the IQR. Sometimes people may want to mention the extremes. So in this case, if we're using the median, we can go ahead and determine the IQR. The IQR is given by Q3 minus Q1.
So for
the
this
mean rank doesn't have any
example, how would
measure of
work this?
spread. How would you work out what?
The IQR, the Q3 minus Q1 from this example.
So you go back to the descriptive table. So these are your Q1 values here. These are your Q3 values. And you're just subtracting. So Q3, IQR, Q3 minus Q1. So for this one, it's 164 minus 136. And this one, baseline, 177 minus 142. Good?
Yes, ma'am.
All right. Good. Where are we now? I was supposed to say one more thing here. I was supposed to say one more thing here. Okay, so in this case, it's okay. We'll come back to it. Let's hope I get it before we end. All right, so this is going on to Jabari's question. So last week when we did the sign test, it says this was the p-value for a two-tailed test, 0.180. And this week we did the Wilcox sign rank test, and this is our p-value. So this p-value said, do not reject H naught. Not reject H naught. The drug does not lower blood pressure. This one says, reject H naught. It's the same data. Reject H naught. No, we shouldn't say lower because this is a two-tail. The drug does not make a difference. The drug does not make a difference. Doesn't make a difference. Reject H naught. The drug makes a difference. All right. How do we explain that?
More into consideration than the sign test.
The Wilcoxon takes more into consideration than the sign test. So that's why sometimes they say the sign test tends to waste the data. And there's another question that I have, but I'll wait until we do the Levine's example. So the answer for this is that the Wilcoxon sign rank test took into account the magnitude of the differences to some extent, while the sign test did not. It did not take into account that the magnitude of the difference. So that's one thing there. We're gonna leave that one right there. Let's do the levying. So we're gonna look at the smoky, go back, the smoky days before and after.
Was that for the statistic for the reject age, not the. What's after the?
The drug made a difference.
Thank you.
You're welcome. So we're gonna go to the levying database and we are gonna determine if the intervention made a difference in the number of smoky days. So let us do that straight away. Oh, I actually have it here. So the output is here. We can just look at it. So this is the descriptive. These are the descriptives. And this is our Wilcoxon signed rank test. It says the number of smoky, so the difference was defined as the number of smoky days per year post-intervention minus the number of smoky days per year pre-intervention. So what are we expecting? The question said we're expecting. Right, so it says whether any differences occurred in the number of smoky days post and pre-intervention. That's the first thing we're trying to answer. And the answer is? There was a difference. So the answer is yes, based on the p-value being less than 0.001. Good. Last week when we did this test, the sign test showed what? When you did the levying test on.
There was a difference, man.
There was a difference.
No, there was a difference.
But there's more, but this is also saying the same thing too. Yeah. That there were more smoky days. But what I want to show you is the sign test with a sample size of 9 didn't pick up that there's a difference, but the Wilcoxon test did. The sign test picked up that there's a difference with a sample size of over 1,000, and the Wilcoxon test also picked up that there's a difference with a sample size of over 1,000. So this kind of drives home the point that in using a test like the sign test, if a difference exists and you really want to pick it up, your sample size will have to be extremely large. If it is small, you run the risk of committing what now, type 2 error? Or type 1. Not rejecting age not when you should have. I think that's type 2. But double check it. Don't quote me on that one. But that is really the take home point on that one. Say what? Any questions, guys?
Watch over the video.
I feel like I surprised myself. Any questions? Jody, what are your questions? What are you looking for when you're watching over the videos? What do you want to look for? Yeah? Go ahead, Alex.
Good afternoon again. So it's just a very random question. So like, could select this topic for my exam. Not talk about it. I describe what we do and interpret it. That?
Yeah, that's it. So you don't have to describe the SPSS part until we give you, we'll ask you to demonstrate the SPSS bit. So you don't have to say, you go to analyze this or that. You'll be able to demonstrate that. So you'll only be able, so you will only need to talk about like hypotheses and how to determine it, what the variable is, the lowest variable, the lowest level of measurement that can be, that you can use for this test. and how the test is actually done in the background, the theory underpinning the test. And then when you're ready for the SPSS part, now we'll ask you to demonstrate it and interpret the output.
Then you ask me another random question on any other topics that we've
From
covered.
a different topic. Right, from a different topic that we've covered. That's right.
Excuse me, Mrs.
Any other
Trinidad,
questions?
can you go over that
Yes,
just one more time?
What Alex was asking?
Yeah,
Okay,
the
so
expectation for the exam.
if for example you chose this topic for your topic on exam day, you will come in and you'll talk about what we've done in the first half of the lecture, not including the SPSS bit. So when you've spoken about the first half, then we will ask you to demonstrate the SPSS part on the computer, and then you'll interpret your output. And then after that, we'll ask you questions based on a different topic that you've covered in the course.
All right, thank you so much.
You're welcome.
Mrs. Chinbele, for the Levine's test, could you demonstrate how would make the output for the smoky just similar to
Sure.
what you have here?
That's fine. So in the Levine's database, you go analyze, non-parametric tests, legacy dialogues, two related samples. So you're gonna click on two related samples, and our handout has post-intervention minus pre-intervention. So it means that we want post-intervention to be variable 2. So we're gonna transfer pre-intervention first. So number of smoky days pre-intervention. And then post-intervention, we'll go over to variable 2. And then we click OK. Oh, you didn't go on the descriptives. So you go on options and you click off descriptives and quartiles, and you should get the first table as well as these. You're good, Vanessa?
Yes, miss. Thank you.
All right, good. All right, guys. Okay. So guys,
The final thing we're saying in conclusion that intervention worked.
The intervention
because the
made a
p-value was
difference,
less
but
than
not
0.001.
the intervention made a difference, yes, but not in the way that we wanted it to be. So you realize that you have number of smoky days post-intervention minus number of smoky days pre-intervention. So if the smoky days post-intervention are less than pre-intervention, which is what we would want, then we're expecting to have more negative ranks. But right now we have 569 compared to 729, which means that we had more smoky days after the intervention than before.
Yes, miss, I've seen that.
Okay. And I think I remember what I was supposed to say. So the mean rank. So the idea with the mean rank is the greater the mean rank, the greater the magnitude of the differences. Because remember, we had to order them, then rank them. So higher differences would have gotten higher ranks. And so the idea is that the greater the mean rank, the greater the magnitude of the differences that you would have been experiencing. And here it is saying that magnitude of the positive ranks greater than that of the negative ranks, mean we had more smoky days after the intervention. That's the idea. All right, guys, if there are no other questions, that's it. Thank you for your patience. Just to remind you that we're gonna have class on Monday afternoon.
That's a
I
2
think-
or 4? What did we agree at?
We agreed on 2. I'm gonna send the table. I was just waiting on a little bit of confirmation. So far, all the days are fine except I think on the 8th of April, but I will keep you posted as to whether or not we're gonna have the session on the 8th of April. Right, the other sessions that we had. But I'll keep you posted as to what
Okay,
so far,
miss.
Dr. James and myself have confirmed the other dates.
What different potential exam days again?
The 10th of June, 19th of June, and the 10th of July. The 19th of June and the 10th of July. The 19th of June is designed for students who want to get over their exam and just be finished with it. And so I'm gonna also send out that link as I'm finished here so that you can fill in your ID numbers on the date and time that you wanna do your exam. You don't know yet? Well, if you don't know and you don't fill it out, then you're gonna have to take what is left.
Oh.
Which is most times 8:30 in the morning. That is perfect for you. All right. So, I think that is all the housekeeping that we have to do. Thank you so much for your time. On Monday, we're gonna do 2 topics because we have 2 sessions, 2 to 6:30. So we're gonna do Wilcox Sum Rank and Crystal Wise. We shouldn't need 4 hours to finish it all because you guys have been doing well so far. So see you on Monday. I'll be here, yes. I plan to be here.
Online challenging.
I'll be here. Yeah, I'll be here. All right, guys, have a good weekend. I don't think Sebastian wants to sign on. Based on what's happening.
And also too.